All right, today we're diving into this really fascinating paper called Disc Game Dynamics. And let me tell you, it completely flips the script on one of the most basic ideas in evolution. It basically says that when it comes to competition, we've been looking at the wrong map this whole time. So yeah, let's get into it.
So we all have this story baked into our brains, right? The story of evolution is this constant climb, this race to be the best. But what if that's not the whole picture? What if survival of the fittest is, kind of a misleading way to think about how competition actually works? The idea that's super popular, even with a lot of scientists, is this thing called a fitness landscape. Just picture a mountain range where all the peaks are like the best possible strategies or traits. In this view, evolution is just the simple process of a population, slowly but surely, climbing its way up to the highest peak it can find. It makes sense, it feels right, and it points to this idea of steady, upward progress. Okay, but here's the massive catch. That landscape, it's not sitting still. In any real competition, I'm talking predators and prey, rival companies, even AI agents learning a game, your success, your fitness, depends completely on what everyone else is doing. The second your competitor makes a move, the very ground you're standing on starts to shift. That peak you were so busy climbing, it might just turn into a valley. So a much better way to think about it isn't a landscape, it's more like a seascape. You're not climbing a solid mountain, you're trying to stay on top of these constantly moving waves. And on a seascape, there is absolutely no guarantee of progress. A brilliant strategy one minute can be a total disaster the next. The whole idea of a single, stable fittest becomes really fluid. And this is really getting to the core of it. The seascape feels chaotic because strategic advantage isn't always a ladder, where A is better than B and B is better than C. In so many real-world systems, it's actually cyclical. I mean, just think about the simplest competitive game ever. Rock, paper, scissors. There's no best move, right? Rock beats scissors, scissors beats paper, but then paper beats rock. Any group of players doing this isn't going to climb to some peak strategy. They're just going to cycle around and around forever. And it turns out this kind of loop is way, way more common in nature and economics than some simple pecking order. And this isn't just a small detail we're glossing over. As the biologists Martin Nowak and Carl Sigmund put it, when you only focus on that static landscape, you're literally ignoring half of the whole evolutionary machine. You're forgetting that the players are changing the game itself as they play it, which means we need a totally new model. So that brings us to the big question, the mean challenge these researchers took on. If the whole fitness map idea is wrong, what do we use instead? How in the world do we find the right map? How can we create a coordinate system that shows us the real, hidden structure of how these competitions play out? Usually we describe competitors by external things, like how big they are, how fast they are, how much money they have. But that's all messy stuff. It's hard to get a clear picture. So the goal here was to find intrinsic coordinates, to define a player not by what it is, but by how it plays. The dream was to find a new mathematical language where all the complicated rules of the game suddenly become simple and predictable. And they found it. They call it the disc game. And it's this beautifully simple two-dimensional game that works like a fundamental building block. In this game, every single strategy is just a point on a 2D disc. Your advantage over someone else? It's just determined by the cross product of your two positions on the disc. It's a simple bit of geometry. You can think of it as the atom of all strategy.
What's so cool is that this model turns complicated strategy into really simple geometry. In the disc game, your relationship to other players is just about your position. If you're on a line that goes through the center, you've got a clear hierarchy. One player is better than the next. But arrange players in a circle around the center, boom, you get a rock, paper, scissors loop. And that center point, the origin, that's a totally neutral strategy that just ties with everybody. It's a single, simple framework that has room for both hierarchies and cycles.
And here it is. This is the big, profound revelation of the whole paper. The researchers proved that any complex two-player zero-sum game, I don't care how many strategies it has or how bonkers the rules are, can be broken down and represented as just a combination of these simple little disc games. What looked like an impossibly complex mess is actually just a stack of simple, rotating discs.
This changes everything. Seriously. The old way of thinking about evolution was all about climbing, about optimizing. This new paradigm, the one from Disc Game Dynamics, is all about orbiting, about oscillating. The goal is no longer to get to a single peak. The behavior is all about recurring cycles. The dynamics aren't just moving in one direction. They're predictable orbits around a central point.
So remember that chaotic, totally unpredictable seascape we were talking about before? Turns out it was just an illusion. It was a trick of perspective. From this new angle, what looked like random wandering is actually a super predictable system of coupled oscillators. The strategists aren't just splashing around in the waves, they're orbiting each other in this beautiful, predictable dance.
And this is not just a nice metaphor. The math behind this is absolutely stunning. The paper shows that the standard equation we use for evolutionary change, it's called the replicator dynamic, it actually simplifies down into a Hamiltonian system. That is the exact same mathematical framework that physicists use to describe the motion of planets and pendulums and all of classical mechanics. It's just incredible. The evolution of strategies literally follows the same kind of physical laws as planets orbiting the sun.
So why should you care? Well, the applications for this are huge. In biology, this could help us finally understand those endless arms races between parasites and hosts. In economics, it could model the boom and bust cycles of markets, where no one company ever stays on top forever. And for AI, this could be the key to training agents that are actually robust, agents that don't just find one good strategy and get stuck, but instead learn how to navigate these endless competitive cycles.
And that kind of leaves us with this final, mind-bending thought. By just finding the right way to look at the problem, the right coordinate system, we've found that this messy, chaotic world of strategy is actually governed by laws as elegant and predictable as physics. And it just makes you wonder, what other hidden laws of nature are out there just waiting for us to find them in all the complex systems that surround us every day?